So now we look at line regulation and power supply rejection. Which is PSRR. Okay. So sometimes you simply say power supply rejection and you call it PSR also, or PSRR, whatever you want to call it. So we know how do we define the line regulation? DC line regulation. How do you define it? Delta V out over delta VDD. Correct. So we'll try to derive this and see what are the parameters which basically derive this line regulation. So let's go back to the same circuit. So first stage we'll consider GM1. We will put this in the feedback. Then at the output we will consider RC. So this is your RO1, CO1, and then we will have pass transistor with your feedback resistor. R1, R2, R load, and you have C out, and this is your V out. Okay. So for a small signal, this will be grounded, your Vref. So again assume that, so I am assuming here that the output resistance looking into the transistor is basically 1 over R out is negligible because R out is large. So I will just consider, but later you can derive this, but I will just give you an idea how to do that. But it will just complicate your equation, but approximately you will get the same thing even if you ignore it. So R out equal to RO2 parallel with R1 plus R2 parallel with R naught. So assume RO2 tends to infinity, then your let's make this much larger than R1 plus R2. Okay. So R1 plus R2 parallel with R load. So all you need to do, just apply the, so what is the V1? So this is omega, not omega V1. So for DC, if I just want to assume DC, then this capacitor will go away. Okay. So we don't consider that for DC. and if I call it VO1, what is VO1? Just move around the feedback. So this is beta V out. So beta factor you have, then GM1 RO1 V out. Okay. So we'll call it equation number 1. Now apply KCL at V out. So what all currents you have? So one current is flowing into R out. So V out over R out plus you have a GM times. What will be the direction? The sign?
V out means
No.
that computing equation minus VDD. GM.
No, but yeah. So, or I can say VDD minus VO1 GM1, and this current will go inside, so it will become minus, correct? Plus, sorry, GM, not GM1, GM2. So, GM2 is the transconductance of this device. Okay. Anything else you have? That's it, huh? So you have only two currents. If let's say I assume RO out of this, I don't ignore, then you will have to add one more current, V out over RO2. Okay, but right now I am ignoring this because when we do the start considering the kappa, so it will little bit complicate the equation. So that's why just to simplify that I have ignored. So equal to 0. So which means V out over R out plus, and what is VO1? We know from equation 1, beta GM1 RO1 GM2. Okay, correct. V out equal to so V out plus beta GM1 RO1 GM2. I am interested in V out over VDD. Okay. So what is that? R out 1 plus beta GM1 GM2 R out. Correct. So this term is much larger than 1. There are two gains there, huh? So it's basically a loop gain, TC loop gain, nothing else. So I can write this over so this cancels out. So what does it mean? DC gain of first stage. It's not even depending on second stage, your line regulation. And if you remember your output impedance, that was depending on loop gain, first stage as well as second stage. So, if you increase the gain of second stage, then it will improve your Z out, but it will not improve your line regulation. So, if I am increasing the gain, then I would prefer to increase the gain of first stage, so that it will improve both my line and load regulation. Okay. So, GM1 R01 is gain of error amplifier. First stage. Okay. So, now we will include the capacitor and we will derive it again and see what happens. So, if I am interested in only response within UGB, then we can ignore the output cap if your omega p1 is dominant. So, we will start I mean, I could have done with that, but it will seem we already know that we did yesterday for Z out and we considered both the poles, and ultimately at the end we had to ignore one. So, now in this case just ignore from the beginning, so that your derivation itself will get simplified, and then once you get the derivation for first pole, then you know how where the second pole is, and you can do the Bode plot right away there. So, this is your omega p1 and omega p2 is here. So, for if this is CO2, for omega less than equal to omega UGB and omega p1 is dominant, we can ignore CO2. Okay, so what I will do, I will just cut this. So, now what is VO1? Beta GM1 R01, and now you have a pole 1 plus R01 CO1 S, correct. So, that is the only modification you have. Now, write KCL at, apply KCL at V out. So, again do the same thing. Let's just copy this, we will not write. Okay. So, now VO1 will replace with that. Okay. So this term is large, this term is much greater than 1. So we can ignore 1 from the numerator. So we can write it let's take this so V out and take beta GM1 RO1 R out common. So we have R1 C1S divided by beta GM1. This should be GM2 here, huh? Okay. So GM2 equal to VDD GM2 into 1 plus R1 C1S into R out. R out is cancelled. So V out over VDD so this GM2 should also get cancelled. Yeah, so we took this whole gain outside, huh? So this should have a GM2 term here also. Beta GM1. Correct? So what is your DC gain here? Beta GM1 sorry 1 over, because this whole thing will go on the right hand side. So 1 over beta GM1 RO1, and this is same as what we had in the previous case, if you remember, DC. So the only additional term will be your poles and zeros. So your 0 is at R1 C1S, okay, 1 plus what else you have, R01 CO1S divided by okay. Now we know omega P1 is R1 over R01 CO1 and my loop gain is A0. What is A0? Not the loop gain, the basically the amplifier gain. GM1 RO1 GM2 RO2, and loop gain is DC loop gain beta A0. Okay. So I can write V out equal to, sorry, V out over VDD transfer function 1 over okay. Now this, if you remember the output impedance, it's quite similar, huh? Yeah, in fact it's same actually. The only difference is the DC gain.